So our next speaker is Dr. Manjakkal. Dr. Manjakkal is a lecturer at Edinburgh Napier University with extensive experience in wearable energy storage and electrochemical sensing. He has authored over 70 peer-reviewed papers and is one of the global winners of the 2024 results in Engineering Young Investigator Award. So today's Dr. Manjakkal's presentation entitled Flexible Electrochemical Capacitors and Sensing is going to focus on the growing demand for wearable energy autonomous sensing systems. He will discuss the design of flexible electrochemical capacitors and sensors for monitoring physical and chemical parameters, particularly in health-related applications. So, Dr. Manjakkal, thank you once again for accepting our invitation, and the floor is yours. You can share your screen.
Thank you so much, Irene. So I'm going to share my slide. See. Is it visible?
We can see your screen in full presentation mode. Yes, thank you.
So I'm going to start then. Hello all. My name, I hope she already introduced me. I'm currently working at Edinburgh Napier University. Before it's the last 2 years I am working here. Before I was in the Glasgow University as a research assistant and also European Union project, medical project, scientific project manager. So today I will share some of my work which I done last few years and some of the work which I am doing currently also. Unfortunately, I'm not providing a detailed presentation of a 2D material. I know this conference is particularly about the 2D materials.
Sorry, Dr. Manjakkal, we cannot hear your voice clearly.
Okay.
I can hear him clearly.
You can't?
I can.
Okay.
I think it's more clear now. Yes, go on, and we will see.
So I will. What I'm trying to say is that because in 2D materials, there are some more material we are now currently working, and it is under consideration of some important channels. So I'm not going a detailed discussion about some of the 2D materials, our recent progress. So, but I would like to discuss with you some of the flexible energy storage devices and its potential for sensing. And my major research work is on electrochemical sensing and electrochemical capacitors, but electrochemical sensing today is limited in presentation. Okay. So coming back to Edinburgh Napier University, we are in the heart of Edinburgh, where we have 3 campuses. One is in Christian campus, another is City Hill campus, and our third one is Craiglock campus. I'm working in this Christian campus here. And where our major engineering and engineering research work is going on. Okay. In this university, I am a research-oriented lecturer. Means I'm mainly focusing on the research team. Okay, and I have a team. My team is called Napier Sustainable Materials Research and Technology Smart Group. Smart Group is mainly focusing on, we are developing our own materials, okay, mainly composite-based materials. And those materials we are trying to, like we are preparing in paste, in a thick film paste or a gel material like a thin film material for the solid spinning, or spin coating method. And also in a screen printing approach, we are developing various types of flexible or non-flexible electrodes for sensing and also for energy storage devices. Okay. One of our major research now currently, one of my students is focusing on 3D printed based electrodes, especially soft material for a flexible and stretchable application. Okay. So we are preparing our own material for our development of sensors. And then we develop various types of sensors, for example, biosensors and electrochemical sensors for a healthcare application and also for pollution monitoring basically we fabricated the sensor in a different substrate, like a textile or a flexible version, and then implement this for a various sensing technology. So one of the crucial problem I found in my research work is that when we have a wearable sensing or a miniaturized sensing, how can we power for a stable operation? How can we power? So what I did that I developed various type of flexible electrochemical capacitors as a power source to operate such a low powered sensor. It's not for a high powered application. It's mainly for a low powered like nanowatt. And even we tried in milliwatt power range as well for some of the flexible electrochemical capacitors. So we developed various type of electrochemical capacitors in our laboratory to operate these sensors. And then we integrate all these system it's a representative figure, okay, where we integrate all these system in a system under energy storage application, okay, like an energy autonomous sensing system. Then see, in all the electrochemical devices for sensors or batteries or supercapacitors, we know that there are various components, especially the hardware and everything. So what I am trying to do that is trying to develop a new bio-inspired sensing system. That means that, for example, you know, in a human body, fluid, the ions are the signal carriers as compared to the other senses where electrons or electrical aspect. So to create a more bio-inspired sensing system, in this electronic-based sensing, we are now electrochemical technology. What's the electronic-based system, the sensors or energy storage devices we have?
Dr. Manjakkal, sorry again, we cannot hear you clearly. Can you go closer to the microphone, maybe?
One minute, let me check it out. Hello?
Your voice is great now,
Okay,
but
can't
we
hear you.
cannot see your presentation. Ah, great. We can see now the presentation. Thank you.
Hello, can you hear me?
Yes, yes, very clear.
Okay. So, we used various electrochemical sensors or electrochemical energy storage devices in the scenario of an ionotronic based sensing system. This is the recent our progress in this area. I will give a small description about what we are doing in ionotronic based sensing system. Okay, so this is the overall summary where we are developing our own materials and fabrication for various application and sensors and, for example, sensors, actuators, electrodes fabrication, and then integrated system, and also in healthcare and early prediction for or in a water quality or pollution monitoring application. Some of the representative publications are also shown here. Okay, where we reported our work. Okay. So, when I'm going to detailed discussion about the electrochemical capacitor, I would like to share with you some basics, okay, about the electrochemical capacitors or a supercapacitor or an ultra capacitor, we can say, whatever the word, okay. So, when we are talking about the electrochemical capacitors, so in my point of view, we are thinking more about the application-oriented technology, where the advanced application where you need a miniaturized or a conformable or a flexible version of energy storage system, okay, and which is non-toxic or which is producing less heat, less weight, or you can integrate anywhere, for example, in a wearables or in a processes or in implantable application or robotics, drones, microsatellite, like a sustainable technology in the future technology where we need a power is a critical component, especially when we are focusing towards all these application. Low power to high power devices are there, various components are there. For all this proper operation, you need a long life cycle energy storage devices as compared to the battery. Okay, we know that battery is the superpower device and super energy density and everything, but we need to try to focus this on a more application oriented, especially for a confirmable application. So when we are focusing towards this, there are one of the critical parameters where is the material and performance wise. Okay, so this is a basic Dragon plot, as you know, all this one, and which is mainly focusing where the fuel cell and batteries energy density. We know that it is a very high energy density. My aim, or every researchers who's working in supercapacitor electrochemical capacitors, aim is to reach the energy density in terms of a battery and power density in terms of a capacitor. Okay, we are trying to achieve that in a supercapacitors in performance wise. Okay, and with them, one of the major advantage of supercapacitor is, or electrochemical capacitor, is the fast charging and discharging with a short interval of time. But when we are considering in material aspect as well, because when we are focusing towards the next generation of energy storage devices for a sustainable development or a zero carbon emission, we need to focus more on the available materials, because as you know that the in energy storage is critical for various application now, especially the boom of electric vehicle and everything. So the rising demand for the various materials is very high, and it eventually leads to changes the environment issue or the cost wise things as well. So we need to focus more towards technology where we can develop a more compatible or more powerful performance energy storage device with using sustainable materials, or like in various forms, like for example in 1D, 2D, or 3D. Also, which is in a various type of material like carbon polymers or metal oxides, like composite structures. So electrochemical capacitors are significant for various all these devices. When we considering a flexible version, okay, there are various there are multiple industries now developing supercapacitors for various application. But when we are focusing towards more on a flexible version, there are only limited one because of the performance of the devices or its implementation. Okay, so when we considering a flexible version of an electrochemical capacitor, as you can see here that there are various material for various components required. For example, there is a material for a substrate. We need a flexible version or a stretchable version of a substrate. And also in a supercapacitor, there are majorly there are two electrodes. One is in two active electrode in a depending on the type of a supercapacitor. For example, in a symmetric supercapacitor, similar type of active electrode, or an asymmetric type of electrode, different type of electrode, or a hybrid one like a battery type of electrodes are using. So all those electrons need to integrate with the need to deposit on the top of a current collector, where the electron transition to the external circuit, or the reaction can be in a proper operation. Okay, so you need a substrate and current collector. So normally in a flexible version of energy storage devices, we can use different type of flexible version of current collector. I'm mainly using graphene based current collector or ITO based current collector. You have a possibility depending on your application, or depending on the implementation of various devices. You can use silver or gold nanoparticle, or other semiconductors like 2D semiconductors, improved 2D conductors you can also use. Okay. In addition, with a current collector or a substrate, you need an active electrode. Okay. You can see here there is a positive or a negative electrode, or both. We not fix one is the positive or negative, especially in a electrochemical double layer capacitor. But depending on pseudo capacitor or a hybrid capacitor, we say one is a positive or one is a negative. But commonly we say that it's an active electrode. So active electrode, normally we use carbon metal oxide polymers or conducting polymers, or a ceramic based materials, or a perovskite based material like a composite structures, like various materials you can use for a electrode materials. Okay, and then moving towards an electrolyte. Okay, I'm not showing here separator. Of course, as separator is one of the critical one. But if you are considering a gel type electrolyte in a flexible version, you don't need a separate separator. Okay, means to overcome the short circuiting, you can use the gel based electrolyte as a separator and an electrolyte. Okay, so, or you are using we normally using cellulose based separator, or there are cell guard based separator. There are many version of separators are also reported. In terms of electrolyte, depending on the type of your application, for example, if you need an 0.8 volt operation or a 1 volt operation, a liquid based electrolyte is always the best performance because of the aqueous electrolyte there. And there are solid electrolyte, gel based polymer electrolyte also there, and also there are ionic liquids are using, an organic based electrolytes are there. Like there are various type of electrolytes are reporting for a various application. Okay, and then we implementing this for a various demonstration, like wearables or robotics or electric vehicle normally do an LED operation or something like that's a very preliminary one. But once you want to operate for a sensors like a pH sensor or a glucose sensor, you can integrate this your super capacitor with this one. But the problem of here in electrochemical capacitors, I noticed multiple times is that self discharge of the device, or the low charge density or low energy density of the device. So we in our group we are trying to develop various type of composite material, various type of electrode material. Like now currently we are starting with the 2D material, TMTC, transition WS2 based material, or a metal organic framework. We have recently one work on a metal organic framework based material to overcome the self discharge or enhancing the energy density. Okay, so coming towards how can we monitor, or how can we evaluate a supercapacitor? This is another major important thing. Okay, so in the previous figure I mentioned you there is a there is an electrode. Okay, you can see there is an electrode, there is an electrolyte, and there is a current collector. Okay, so as compared to traditional capacitor, in electrochemical capacitor, the full reaction happening on in the electrode electrolyte interaction. But you can see from here that there is a current collector, there is an active electrode and electrolyte. So depending on your type of electrode, for example, if you are using an electrochemical double layer capacitor like a graphene or a carbon based one, there is an electrochemical double layer forming. There is no redox reaction. But when you are using a metal oxide, there is a diffusion of ions or a redox reaction will happen. And in that case, more high capacitance will be observed. So depending on the type of here, the reaction here, you will get the performance. Okay, and then when we have an electrode electrolyte interaction, we always look forward what is its energy density. Okay, and what is the power density. So means the maximum power density or energy density which you can generate from the electrochemical capacitor. But majority of the case, maximum energy density or the maximum power density may be not useful for you to application, because there may be a usable energy density, because if your device there may be always some voltage drop, or there is a sudden drop in the energy density. So we always in my work I always try to keep the energy density a stable operation. For example, if it is showing in a 0.8 volt device, if this 0.8 volt I can apply, but in a proper operation, maybe I will use the 0.5 volt, and basically the energy density is varying accordingly. Okay, so there is a proper energy density we need, and we are always looking forward to calculate the energy density. We always comparing our performance like this. Okay, so this is the basic equation which you all know. For example, capacitance we are measuring. This is from GCD analysis, galvanostatic charging discharging analysis. Means if someone is the basic in this area, so what you are doing that the EC performance, you are mainly in using electrochemical workstation. There is a cyclic voltammetry, electrochemical impedance spectroscopy, and galvanostatic charging discharging analysis. All these three tools you can use for measuring the energy density and specific capacitance of your device. So so I here you use the equation from the GCD analysis for a two electrode system. Okay, and there is a energy density also and a power density. But in some cases, in a charging discharging analysis, there is a voltage that voltage drop due to many parameters in that. I will discuss with you that one. Okay. Then in such a case, we consider the voltage drop also. Sorry, I don't know why it is showing two lesser point here. In such a case, we are using energy density. The capacitance is voltage, considering the voltage drop. Okay. So basically, in the energy density calculation, we need a specific capacitance. So what is the parameters when you want to fabricate a supercapacitor? What are the major things you want to check for a specific capacitance enhancement? Is that the active material which you are going to use? Okay, and the method of fabrication which you are going to implement. For example, if you are planning to develop a thin film or a thick film, where the mass loading of the active material is changing, and also you can see that there is a strong influence on there. That means the energy electrode density. You need to, depending on your type of application or depending on your type of implementation, you can use a different type of material, and the specific capacitance is purely depending on these materials influence. Of course, it may have influence on the voltage electrolyte as well, and where the operating voltage have a significant reaction. Okay, so the operating voltage is another one where in the equation you can see there is a irony. Did you see the laser point in my presentation? I don't know. Yeah. So there is an operating voltage. That operating voltage shows depending on the cell configuration or the electrolyte material. Okay, as you can see here that depending on the type of the electrolyte, the operating voltage could be varied. Okay, and then one of the important parameter for in a supercapacitor performance evaluation is the equivalent series resistance, where the voltage drop or the power loss can be happen. Okay, so here can see that it is depending on the various type of material, where active materials, the type of active material you are using, on the experimental method like packaging or fabrication approach, or the current collector or the dwelling time, like various parameters which can influence on the equivalent series resistance. And when equivalent series resistance is very high, the power loss will be very high, or the voltage drop will be very high. Okay, so we evaluate the supercapacitor performance using electrochemical impedance spectroscopic analysis, where you did the nickel plot or bond plot or whatever the impedance data you observed, and where you can find that depending on the type of electrolyte interaction, okay, the resistance of the material will be changed. Okay, and that resistance of the material depending on the slower diffusion of ions or the electrochemical double layer formation, where you can clearly determine from the impedance analysis. And the equivalent series resistance also you can calculate from the nickel plot, where the intercept is. Okay. Another one is the cyclic voltammetric analysis, where the redox reaction, or example, if you are using an electrochemical double layer based capacitor, this CV loop will be almost rectangular shape. That means there is no redox reaction. But in some cases, we are using metal oxide, then a pseudo rectangular shape is observing because of the redox reaction of the material. Okay, and depending on the operating voltage, you can change the CV analysis as well. Okay, and then there is a GCD analysis, where you can use them discharging, and where the capacitance or efficiency you can calculate, and there is a voltage drop that also you can observe here. Another important parameter in a supercapacitor evaluation is when you are using in an electrode, where the metal oxide or a graphene composite are there, then there are two type of reaction can occur. One is the capacitive contribution due to the redox reaction, and then the diffusive reaction, where the electrochemical double layer formation. So you can evaluate the charge storage in each supercapacitor electrode by using a particular equation, where a dense method or some other method, where you can calculate this. Okay. So this is the basic evaluation approach when you are developing a flexible electrochemical capacitor you want to. In addition to this, you need to measure in a flexible version the bendability of the device, long charging, discharging, like Coulombic efficiency, like other parameters also there in the evaluation. Okay. So in my work, what I noticed is that depending on the type of the electrode, for example, I developed a carbon-based electrode for a electrochemical, like a 2D material, like a 3D structured graphene form, a graphite polyurethane composite based electrode material for my device. Okay, depending on the type of the electrode which I used, the operating voltage and the electrolyte there, the performance varied, and I used, for example, in a graphene form, one of the device I got, you can see from the impedance spectroscopic analysis, the variation, the resistance is in the very low range. That means it's a better electrolyte interaction. But the energy storing of this electrochemical double layer is very limited, and I observed the energy density, the specific capacitance in 8 millifarad per centimeter square, but the operating voltage is limited. And in another case where I developed a graphite polyurethane, then there is a thick film based paste, and the electrode configuration here is a different, and that cell configuration changes the voltage. And also I got another gel based electrode here, and then in a graphite polyurethane composite I got a different performance, and which I reported in another 2 papers, and one is in a patent. Another version of the electrode which I am developing in a flexible version is the graphite or a metal oxide based electrode, or a metal oxide with a composite like a metal oxide with P.PSS, or a metal oxide with the graphite version. So you can see from here that there is a copper oxide with graphite, and which have a different performance as compared to the other devices where the capacitance is varying depending on the voltage or the electrolyte. I also used here other electrolyte were sodium chloride or a NaPF, NFC, calcium chloride. Depending on the type of electrolyte, I noticed that the performance of device is varying. In another metal oxide, where along with my colleague did, were a metal oxide with P.PSS in a stretchable version of a supercapacitor, but I found that very high performance. This is due to the method of fabrication we are using here. In this first version, these 2 version, in a graphite polyurethane or a CU2, we use thick film technology. In another version where we use the electrochemical deposition method, where the nanoparticle or a more oriented based material is forming, and which enhance the performance. Further, I also did some of the work on along with my students, and we did some of the work on conducting polymer based energy electrochemical flexible electrochemical capacitor, where one is on P.PSS, and where we developed these capacitors in a textile based substrate, and another one in a polyaniline, and also we did in polythiophene based devices as well. As you can see here that in more wearable application we use other electrolyte here, a human set different electrolyte like a human body fluid application, where we found a very good performance for a set monitoring sensors application. Okay, in a polyaniline based devices, we observed that depending on the conductivity of the polymers as compared to polyaniline or polythiophene, the electrochemical performance is changing. Okay, so we basically compared all the type of material here. Now currently we are doing in a perovskite based material to further enhance the performances, or we are also now trying to develop this with a controlled material synthesis, where nano is a flexible version of application. Because one of the major problem we noticed that in a composite or a paste based technology, the additives or the binders which we used are influencing on the performance of electrochemical capacitor. So in the previous one, we compared various type of materials. But what we done recently in collaboration with the Glasgow University with the Professor Kumar and team, okay, we developed a 3D printer. This is not a flexible version. Okay, I just want to show you one of the interesting result here. But if you are interested, we can do further more here on a structural oriented material. Okay, for example, we have a different 3D printed 3D printed electrode, where we create the porosity by using the 3D printing technology. So you can see from here that in the same images, there is a bulk sample without any pores, and then we create small pores and large pores, and then we coat this with a conductive polymers also. And then we used this for a electrochemical capacitor application. For example, you can see from here that we took PVC substrate and attached the PVC with a current collector in a graphene sheet, and then one side we use the electrode, and then we attach the 3D electrode here. So you can see that 3D printed electrode we attached on a step, and then we bonded this one with a conductive polymer. then you can see here that depending on the type of the electrode we used, for example, when we have a bulk sample, there is no porosity. What will happen is that when you drop an electrolyte, the electrolyte is mainly reacting on the surface, means all the area, all the surface where the electrochemical reaction is happening, means the electrochemical active surface area. This is one of the most important parameter in electrochemical capacitors. But when we have a porous structure, the ions or the electrolyte are diffused inside the porous structure, influencing on the enhancing the electrochemical active area. And once we have a conductive polymer on there, what will happen is that depending on the conductive polymers, the electrode is further reacting with these conductive polymers and also in the porous structure. So the conductive polymers, when we are dropping on this 3D printed electrode, it will diffuse inside the 3D structure, and it will enhance the active surface area. And then once we compare this one, we noticed that the large pores, okay, with a more oriented structure with the conductive polymer shows better current acquiring by using CV analysis, and it shows a very high capacitance in the device performance as well. So this is in a rigid version. You can replace this rigid version with a flexible version of a 3D printed electrode. One of the issue here is that the bulk size, maybe some of the dead volume is influencing on there. So this is again depending on the type of 3D printed material you are going to use. For example, you can develop a 2D structured based 3D printed electrode and with a high conductivity of the material. Here we use the material called polyethylene ethylene ether and multi-wall carbon nanotube based electrode. So you can use different type of material. Only in one of my PhD student, he's trying to synthesize a new composite electrode where more conductive nature of 3D printed electrode with a flexible version, and where we can introduce the different porosity or the different or the different shape of the pores in electrochemical application. Another case study, so you can see here that we collaborate with another institute in Poland where we investigated how the performance of a conductive polymer, as I mentioned in the previously, for example, we coated in a spin coating up on the top of a graphite polyaniline polythiophene based conductive polymer. And then once we coated this one, we noticed that depending on the type of the polymer and depending on the type of the electrolyte we are using for the electrochemical application, the performance is varying. For example, here you can see the electrodes for a polyaniline and polythiophene based material, where the polyaniline with H3PO4, you can see the charging discharging, where the Coulombic efficiency is much better as compared to the polythiophene. And the performance also shows that polyaniline with H3PO4 shows much better high capacitance as compared to polythiophene. Due to the more redox reaction or the conjugated polymers in this type of reaction can occur here in a conductive polymer. One is the conjugated polymer reaction, or another is the electrochemical double layer reaction because of the conductivity of the polymer. Okay. We tested this with H3PO4 and HCl. You can also use this with another gel electrolyte, which we did not done yet. We are trying to focus this with different room temperature ionic liquid, and because conductive polymer is one of the good material for a flexible application, and where you can easily incorporate with other 1D or 2D materials to enhance its performance, which we observed previously with our metal oxide with the conductive polymer combination. Okay. Then further to this, as I mentioned you previously, the separator is one of the most important parameter in the electrochemical devices. Okay, so there are different type of separator when we are using for a green energy application or a clean energy solution. You need the material which is fabricating using more cellulose based material. So what we done that we are using some plant based the water plant based material, water hyacinth, okay, where the cellulose content is very high. One of my PhD student, he convert that into a bilayer separator membrane. And then what we done that, as you can see from here, that there is a double layer formation of this material, and then this type of material we implemented for a primary supercapacitor or a secondary supercapacitor electrode, where in a primary supercapacitor, in a filter paper, like the electrode fabricated on a paper-based supercapacitor or a paper-based electrochemical capacitor, where we deposited the paper on the top of a paper, a manganese electrode, and then the separator with a potassium hydroxide as an electrolyte, and another separate. It's like a hybrid supercapacitor. Okay? In the second, because this is a single use application, but if you want to use a multiple application, what we did that we use a silver conductor as a conductor, and then use the electrode material on the top of this. Okay. Then we observed that here is the fabricated devices, like a ultra flexible one, copper based electrode, and here is the electrode layer. And we found that when you are using the separator, one is on the top one you can see in the cell guard, bottom one you can see the our bilayer separator, the cellulose one. So in a electrolyte interaction, the contact angle means the how the electrolyte is distributing is most important parameter to enhance the electrochemical capacitive area, surface area, and also the specific capacitance. And we found that the bilayer separator absorb the more water content than the cell guard based separator. Here you can see some of the semi images of this material. I'm not going in detailed explanation that. And here you can see that the bilayer or the taking of the water layer is much higher, and it have very high visibility opportunities as also. So based on this separator, we fabricated the electrochemical capacitor and cell guard and bilayer, and we found that due to this electrolyte intake of the separator, which shows the electrolyte interaction with the low resistance, and performance wise we noticed that our device shows a very good Coulombic efficiency and the discharge work we published recently in applied material interface, where if you are looking forward more green based energy storage devices in a flexible version or a sustainable application, you can utilize such a cellulose or such as a high water content based material as a separator. Okay. In addition to that, there is another opportunity where you can develop the green energy storage in a flexible version by utilizing our natural resources. For example, different type of bast fibers. And once it's treatment, you can then you can develop the energy storage devices based on that material. This is one of the review paper along with Professor Luis Pereira and the University of Leeds, University Atlantic Technological University, Professor Suresh Sipple. I recently reported in how the natural resources or the bast fibers can be converted into electrochemical capacitors application, where there are limited, you can see that there are limited work is done in this area with the composite material. Still, there is a possibility where you can use 2D material coating on the top of these fibers. Okay, I can show you one example. See, one of the work I did that there is a jute fiber. Okay, I have a jute fiber. That jute fiber I converted to a conductive fiber. And then using that conductive fiber, I developed a new electrode, and where the conductive fiber coated with PEDOT PSS, also a carbon nanotube. You can see here it's like a dual, like a cable type electrochemical capacitor. As you can see here, that's a single cable. Okay. And this is actually converted the jute, and you can develop. And here you can see the FTIR spectrum of this and with the material as well. And then here you can see how the electrode configuration we did. Okay. For example, the fiber is there, and then electrolyte interaction is there. And depending on the type of the electrolyte, the performance is varying. Okay. And this is a best example where we can do this for a smart application. So the natural fibers you can convert into an energy storage devices by using different materials, and then it could be used for a packaging application. Still, there is the problem I noticed here that the energy density is low because of the type of material you are using. If you are preparing a high performance 2D material, you can coat that with the fiber, and you can utilize this. Here I demonstrated where a solar cell integrated on the package with there is a humidity temperature sensor, as you can see from here. The same jute fiber I converted it in humidity and temperature sensor where you can monitor that application. Okay. So when I'm coming towards more towards the wearable application of these energy storage devices. Okay, so during the last few years, I found that there are many critical parameters which influencing on a wearable application, especially sensors and energy case. Okay, one is the sensor select and the low magnitude of sensitivity factor. For example, some of the physical sensors where you are using touch sensor or other pressure sensors, the performance is in, for example, we get 100 nanofarad or 10 nanofarad, and the variation is in the nanofarad per centimeter or per force or per newton or something like that. Okay, uh, the low magnitude of sensitivity will influence the interference by external factors like electromagnetic interference or something like that, and also the hysteresis or memory effect. And when you want to integrate such a sensors to a wearable application, normally we don't like to wear a bulky system in our human body. We need more compact where less components of wires, less wires, and also the power demand. For example, there are different type of electronics there, and it could be also useful for a human machine interaction. And when we are talking about the power demand, you can see that here the sensors, there are multiple sensors which require various uh, sensors which require various power to operate. This is not only sensors, there are different components like analog to digital converter, microcontroller, or Bluetooth based energy storage devices. The wearable physical sensors also there. All these devices require various type of energy storage, and but the wearable, when we're talking about a wearable energy storage or generation means either biofuel cell or a piezoelectric based or a triboelectric one, there is a limitation in the energy density or the power generation. So still there is a plenty of room where we can develop more high powered flexible version of energy storage to operate all these components. One of the possibility where I found that the energy storage itself, okay, act as a sensors, then we don't need an external sensor to operate. Means the whatever the energy producing from the energy storage device, you can use for powering some of the electronics part. You don't need to power for the external sensors. There you need ion sensing or energy coupling. Okay, so for example, this is one of the concepts where recently explore many researchers doing, where the in the ions, where the ions act as a sensing or ions act as an energy storage component using the ionotronics concept, where the mobile ions and electrons the key factors, okay, which you can use it for diodes application or ionic triggered or a field effect transistor, like those things. But the major advantage of such a ionotronic based component is that see, for example, you are using the electric wires, you can replace that wires with the ionic cable, which will be the ions carrier. Okay, such a device, what will happen is that just imagine you have a flexible version of electrochemical capacitor. Okay, there is an active electrode on the top, and the ions are there with the gel electrolyte. So you know that the gel electrolyte, the ions are there, and which will interact with the electrode surface. In a normal case, what will happen when we apply an external force? Okay, when we apply an external force, this electrochemical area or this actual area will change due to the disturbance of the force. Okay, there will be variation of this one. Depending on the force, this ions distribution or the electrolyte distribution or either electrode surface area contact with electrolyte will be varying. We need to investigate, and once we investigate that in a systematic approach, we can use that as a force sensing or a pressure sensing application. In another case, you know that when we have such an active electrolyte, there are plenty of ions are there. These ions can be, depending on the type of the potential you are applying, the ions will be absorbed, diffused or absorbed into the surface. Okay, but in a when we have a external temperature or the temperature of the atmosphere is varying, of course, the packaging is influencing on the temperature diffusion inside the material. But we noticed that with the temperature variation, the more the orientation of these ions will be occur. Okay, and that will lead to changes in the energy density or the specific capacitance of the material. One of the study what we done that we developed a transparent electrochemical capacitor. So you can see from here. This is one of my master degree students. She did this work, and this year we published this work. Okay, where we investigated ITO-based electrode. ITO is, of course, is a commercial material which shows a nearly hydrophilic or hydrophobic character, where we use different type of gel electrolyte, like sodium chloride, potassium chloride, lithium chloride, gel electrolyte. And then based on the electrolyte, this electrolyte interaction will occur. It's a fully transparent one. So you can see from there the 100% transparency. And depending on that electrolyte, we noticed that the electrode-electrolyte interaction is varying. And we observed the better performance in a lithium chloride-based electrolyte with the PVA as a gel, PVA as a hydrogel there, and which shows very low resistance and low impedance value and a high capacitance value. And because of the more ions interaction, okay. And that also you can notice from here that how the electrochemical reaction, the pseudo capacitance of the material because of the ITO. There it shows a conductive material, but of course the metal oxide is there. There is a pseudo capacitance reaction. And depending on the scan rate, you can see that LICL shows much better capacitance for this device. Okay, where you can see that this LICL, this TEC, working as an energy storage device. So you can see the charging, discharging, and the energy density we got almost 0.5 microwatt hour per centimeter square, which is useful for operating a nanowatt for electronics application. But when we apply an external force on the top of this, we found that this capacitance variation is changing with applied force. And when you plotting this graph, we observed a slope, a response in compared with the force. But of course, this is a limited force only you can apply. We are now trying to do that with a high force application. Okay, large area. In addition to this, such a transparent electrochemical capacitance, while integrating with ITO with other electrochromic material or other for display application, you can use this as an electrochromic device also. For example, we recently, along with Professor Luis Pereira in CENIMAT in Lisbon, we read a review article where the electrochromic based application of such a transparent electrochemical capacities. For example, if you want to design a smart room, okay, such a transparent electrochemical capacitors can be implemented, and which will generate energy or which will store energy from the solar cell, and that energy can be controlled where you can implement. And of course, the color changing is due to the electrochromic properties of the material. This is again, this work is going on, and we recently done and improved this work with tungsten oxide nanoparticle, and we are now working towards the 2D material coating of this with electrochromic application. Other supercapacitive ion monitoring, because the transparent one is showing it like a. I want to show you one more thing. Okay, here you see. Here we know that the capacitance is you got in a millifarad range. That means the sensitivity, the magnitude of sensitivity is in the millifarad range here, the pressure sensing, as compared to the nanofarad or microfarad based traditional physical based sensors. There is a almost 1,000 times higher magnitude of capacitance or a higher magnitude of sensitivity observed. This is like a super capacitive. We can say this is a super capacitive sensor. Okay. And we investigated that supercapacitive sensors for a biofluid application also. In one of my previous work, what I did, I developed an energy storage device using a human body fluid, like a human sweat as an electrolyte, where sodium or potassium ions reacting with a textile-based electrode, it generate the energy density, electrochemical performance due to the conductive polymer nature, where the electrochemical double layer or the conjugated polymer of the conductive polymer. Okay, so in a human body fluid, like in a sweat, there's a sodium ions are there, potassium ions are there, or other calcium ions are there. What we can do that we can use those ions as an electrolyte. So you don't need a separate electrolyte. So in such a case, you need to develop the electrode in a textile which can absorb more. Okay, and what we did that we varied recently. We did another sensor where we changes the sodium concentration. For example, the sodium chloride, depending on the in the human, depending on their health condition, the sodium chloride maybe changes. Okay, so the salt means the salt. Okay, so the conductivity of the electrolyte will vary. So what we did that we changed the electrolyte conductivity, and we found that this electrolyte conductivity variation influencing on the energy storing or the capacitance generation of this device. And when we did a variation, and we found that there is a 2.05 millifarad per sodium concentration changes, sodium ion changes in the sensitivity. So one of the work we recently reported in IEEE Sensor Lecture Journal, we are now currently investigating on this application with a, because in a human body fluid, there are multiple ions are also involving. Okay. Addition with those electrochemical sensors, I'm not going in a detailed here. I did some work on electrochemical sensors where my PhD is based on an electrochemical pH sensor. As you can see here, I developed a potentiometric pH sensor, interdigitated pH sensor, and a reference electrode. Also various flexible or a stable or a textile-based body fluid monitoring sensors. Also involved in a various type of physical-based sensors like a biodegradable sensors or a strain sensors. Okay. And these sensors we implemented for various applications like healthcare application or a food and agriculture or a pollution monitoring application. And in our laboratory, we are developing various type of electrodes, various type of devices, and its implementation in various application. Okay. We have some of the equipment in our laboratory where we can develop our materials or develop our electrodes in a controlled manner or in a 3D printed or a screen printed electrodes, and we have the electrochemical workstation to do all the measurement. This is my team, and Mustashan recently completed PhD with us, and he now joined. He was working with me as a postdoc, but now he got another postdoc position. He's leaving, he's left now. And my current PhD student, they are developing. Febin is working on a 3D printed based energy storage devices. Prasudha is working with water quality monitoring sensors using a 2D material. I did not present her work today here because we are under preparation of some of the journal. Hale, I'm a co-supervisor. She is working on a communication side. And Jithin recently joined with us a PhD student where he is developing flexible or a 3D structured. Because all these flexible version, another interesting approach we did that you can see that there are flexible version of electrochemical capacitors. The importance of that one is you can consider this as a part of any structure of an equipment or any structure of a furniture. So we are working towards such a structural based energy storage, especially a flexible version. And the research assistants are there, and they are working towards electrochemical sensors or a piezo-based sensors. Thank you so much for my funding agency where I am currently working in a funding where Carnia grant. They provided some of the where we're developing a piezo ionic based sensors with a machine learning computation. If anyone interested to do more collaboration on that side, you're warm welcome. I didn't present that work here. It's a currently ongoing project, and I'm editing journal. One is in chemical engineering journal, and another is a results in engineering journal. Thank you so much.
Dr. Manjakkal, thank you so much for this enlightening presentation. Actually, we have some questions from the audience to ask.
Okay.
So I will start with the first question. So you gave the substrate example P.PSS. Is this cost-effective, environmentally friendly, and easy to fabricate?
Cost of the substrate is not a P.PSS, it's a conductive material. It's an active electrode material we are using. Substrate is mainly we are using a textile or a PVC based substrate. Maybe I don't know whether I missed the explain. Maybe I wrongly explained that. P.PSS we are currently using a commercial material, so we are not preparing the P.PSS here. So we are using the commercial P.PSS. Of course, the environmental friendly or cost effective is a problem there. It's an expensive material. Of course, I agree with that one. But we are not using that as a substrate.
Thank you. Another question is about the perturbation voltage as well as the range of the frequencies applied during electrochemical impedance measurements.
Okay, so we normally use the voltage range. So voltage range in the range of, for example, 0 to 0.8 or a 0.2 voltage range, depending on the type of your electrode. Okay, and of course, some of the electrodes showing a voltage drop is there. Some of the devices we observed sometimes IR drop of 0.2 volt or a 0.3 volt, like that. Means sometimes very millivolt also. In frequency aspect, we are using mainly from 1 millihertz to 1 megahertz. Of course, we have the facilities here to do the 1 microhertz to 1 megahertz, 10 megahertz range. The problem in 1 microhertz range is the long time for to do the measurement. So majority of the work we reported in 1 millihertz to 1 megahertz range. Why in the low frequency range is that in the low frequency range only you can observe the exact electrode, the ionic diffusion part.
Thank you. What is the possibility of dendrite formation on the materials you just talked during the session?
The dendrite formation, okay. Actually, because we are not using any lithium-based material yet. Of course, there is an electrolyte-based materials are there. There is a redox reaction on the material degradation changing, but the dendrite formation we did not check yet, and we will do that. We will check that possibilities.
And what is the repeatability of P-dot PSS based electrochemical sensors?
Yeah, P-dot PSS, for example, this P-dot, if I hope then Rajan is mainly looking forward that supercapacitive ionic monitoring sensors. Depending on the type of, depending on the amount of electrolyte you are using there. For example, if you are coating this material with a uniform coating or with a limit, the mass loading, of course, the mass loading is important for this electrochemical capacitors. In our approach, we are using the coating in a drop coating or a dip coating method. We have a controlled coating method. So our repeatability is with a variation of a plus or minus 0.2 millifarad or something like that range only. And also we are measuring 5 samples or something like that. So again, it depends on the amount of material you are coating on your electrodes.
Mm-hmm. I think that we have time for 1 or 2 questions. Is there any possibility of use of basic electrolytes for the capacitors?
Is there any possibility use of basic electrolyte for the capacitors?
Any possibility of use? Mm-hmm.
I hope you are talking about basic or base electrolyte, acidic electrolyte or a base electrolyte. Maybe the question is about
basic electrolytes.
Yeah, you can use a different base electrolyte, basic electrolyte for the electrochemical capacitors. So in aqueous based electrolyte or liquid based electrolyte, you can use sodium chloride or potassium chloride or other ionic liquids or a different type of electrolyte you can use.
Mm-hmm. And if we try using energy storage device to act or behave like sensors, how would we handle the signal noise that is produced?
This is a very good question.
Due to external factors in storage material, like temperature variation.
Yeah, this is a very good question. We are now, as I mentioned, there is a temperature influence. We are testing in the storage. This is exactly what I mentioned, the cyanotronic based sensing where we tested this with external temperature. Again, such as supercapacitive ionic based sensors, I found that the amount of material or the electrode fabrication is influencing on the energy storing performance. If you did this temperature variation or depending on the packaging, we can overcome this issue. And we tested with the various temperature from -20 to +70 degrees Celsius as well.
Great. Dr. Manjakkal, I would like to thank you once more for your presence in the webinar series of Infrastructure School and for honoring us once again.
Thank you so much for the opportunity as well.
It was a pleasure. So I will stop recording now.
Okay. So can I leave?
Yes.
Of course. Thank you so much, Irony, for that.
Thank you so much. For our participants, tomorrow we will start 1 hour earlier because we will have an integrated talk with Athena European University's colloquial talks. So within the day, you will receive a new link to watch the first session seminar webinars. So within the day, you will receive this link. And after that, at 11 CET, you will join in the usual link, as always, you do every day for this past week. Thank you so much, everyone. And I will send you the link within the day, the new link, and I will tell you all the information. Okay? Thank you so much again for your presence here.
Thank
See you
you so much.
tomorrow. Bye.